Hello, ladies and gentlemen. With the not meeting this week, it's not an extended spring break. We still have teaching and learning we have to do. And I'm going to do it by videos. I'll get the rest of the details to you by email. But we'll pick up where we left off before spring break, and I'm going to review first order differential equations related to RC and LR circuits. They have this form right here. And this is the solution, general solution for any function, but if FTH, if the function is a constant, then it becomes particularly simple. The trick is to find K1 and K2. It will hold on any interval where the sources are constant. So you have a constant source, you go along, you have a constant source, and then you switch, and you have a new constant source. You're going to have K1 and K2 for this interval, and K1 and K2 for the next interval. They're going to be different constants, but where it switches, the value of the voltage across the capacitor has to be the same, and the value of the current through the inductor has to be the same. That's how we find the new constants. That whenever we have a new interval, the values at the end of one interval become the initial conditions for the next interval. So let's illustrate that. Let's see how this works. We have a voltage source. It switches from 0 to 9 volts and then back down to 0 volts at 0.3 of a second. You can think of it like there's a switch. So here's the voltage source. And there we go. And we have a switch that switches at 0 seconds, it switches up. Then at 0.3 of a second, it switches back down again. And this, of course, is connected to the rest of the circuit over here. The rest of the circuit. Okay. So the way we analyze it is we consider time less than 0. Steady state is when there's no current through the capacitor or no voltage across the an inductor. We can treat capacitors as opens, inductors as shorts in steady state. Steady state, nothing's changing. Everything is settled down. So when time is less than 0 in steady state, the voltage output has to equal 0. When time is greater than 0, the instant time is just an instant above 0, voltage still has to equal 0. But the source voltage, the voltage out, has to equal 0, I should say. The source voltage switches to 9 volts. And so we have the equation K1 and K2 prime. Now let's get some erasing done here. There we go. At 0 volts, at 0 time, at 0 time, this exponential here is going to equal 1. So at time equals 0, K1 prime plus K2 prime have to equal 0. the time constant is going to be given by Thevenin's equivalent resistance that the capacitor sees. Thevenin's equivalent resistance between these two nodes. If we're talking about inductors, we're talking about Thevenin's equivalent resistance between the node that the inductor is connected to. R times C is the time constant for an inductor circuit. Time constant equals L over R. I'll just put it up here. The inductance that is weird that it's not going away. Okay, doesn't matter too much. L over R. Okay. That's the time constant for an inductive circuit. RC is a time constant for a capacitor circuit. It's the equivalent resistance between the nodes that the inductor or capacitor are connected to, which we can see it's 12 k ohms in parallel with the, 6 k ohms in parallel with the 12 k ohms, times the capacitance, 100 microfarads. 100 microfarads equals 4/10 of a second. Okay, let's just clear everything. Discard all my inky annotations. Oops. Get back to where we were. At time equals infinity, steady state, this voltage is going to be given by the voltage divider equation. This is treated as an open. This is infinite resistance. So it's just the 8 k ohms divided by the total resistance, which is the 10 plus the 8, times the 9-volt source. 9-volt source right there. 9 volts. And that's going to be equal to 4 volts. K1 equals 4 volts. And we've already figured out K1 plus K2 K1 prime plus K2 prime has to equal 0. So K2 prime is a negative 4 volts. And we should have the solution, yeah, K1 plus K2 prime equals 0. And then we get the final solution right down here. Now, at 3/10 of a second, we got to figure out what VO is when time equals 3/10 of a second. And you know, we can run through the calculator, stuff like that. There it is. There's the equation. Now we have K1 and K2 double prime. You'll notice that we've got T naught now makes a difference right there. So at 3/10 of a second, we match up this solution down here with the new solution up here. We have to match these up at 3/10 of a second. Well, that of course is K1 double prime plus K2 double prime has to equal this. VO is going to equal K1 double prime plus K2 double prime. That's supposed to be a 2 down there. Okay. Get that all done. The time constants, is the time constant still the same? Yeah, it would be. Thevenin's equivalent resistance wouldn't change. Sometimes it does, by the way, if the switch is connected to a resistor. At infinity, that steady state, K1 double prime has to equal 0. That means at 0.3 seconds, K2 double prime has to equal whatever the value of the voltage is. Oops, get my pen back on. Whatever the value of the voltage is, and it's 2.11 volts. That has to, here it is. This equals 2.11 volts. Yeah. So we've got the solution for after 0.3 of a second. So 0 to 0 to 0.3 seconds given by this here. Then after 0.3 of a second given by this. And before, it's given by this. V naught is 0. The solution between 0 and 0.3 of a second, this, let me erase my stuff so that you can see what the authors put down. Oops, I didn't want to do that. There we go. So the authors, this is the solution from 0 to 0.3 seconds, and then this is the solution after that. Okay. This is a similar problem. I'm going to stop the video now. You guys have seen how we solve this problem. I want you guys to do this problem for practice. And I'm going to end the video at this time. We'll pick up with the next video next time.